Hello folks, and welcome to this video on transverse and longitudinal waves. Now what we're going to do in this video, we're going to define what we mean by these two types of waves. We're going to look at some examples, and then we're going to try and apply that knowledge to a specific example from the field of geography. And we're going to begin by looking at the two GIFs that are on the screen. Now, I should say at this point, I didn't make these. I definitely don't know how to do that. These are both from the wave properties section of the LibreText physics website. So please do go there if you need more explanation on this. I really like these demonstrations because they show very clearly what's happening in the two types of waves. So let's start with the left-hand image. What you can see there is probably the classic form of the wave. Very clear amplitude and wavelength. And what's really nice is you can see the motion of one individual particle, that red dot moving up and down. Now, what this image is of a transverse wave. And specifically, a transverse wave is one where there is a disturbance. So in this case, the motion of the red dot. And that disturbance is at 90 degrees or perpendicular to the direction of energy transfer. So you can notice here in both of our GIFs, the energy transfer is from left to right. But in the left-hand image, my particle is moving up and down. And so, in other words, it's being disturbed up and down. And that is causing the production of our wave from left to right. Now, that could be in any direction. Okay, it could be in or out, which is perpendicular to the direction of energy transfer. So when you're defining a transverse wave, you have to use those terms, that term perpendicular or 90 degrees to the direction of energy transfer. I've seen students before write up and down, and it doesn't always quite fit the definition we need. So some examples, there's loads of examples of transverse waves. You could imagine someone, for example, with a rope, simply oscillating one end, that will generate a transverse wave. And similarly, water waves are also transverse. Now, one that you may not know about is light waves. Light waves are also transverse waves, and what that means is that the light wave is moving from left to right. Then the disturbance, whatever that is, the electromagnetic disturbance, is going to be in a direction which is at 90 degrees to that direction of energy transfer. Okay, so this is transverse waves. And as I've said, a lot of waves are transverse. Now, there are very few of the other type of waves which are longitudinal, and you can see the longitudinal wave on the right-hand side. What I'd encourage you to do is take a second to look at that red dot on the longitudinal wave and think, what direction is the energy transfer and what direction is the particle moving? And when you're ready to go, watch on for the definition of what a longitudinal wave is. If you've taken a second to think about that, you can see there that the particle is moving left and right, but the disturbance itself is also moving from left to right. So this is different to our transverse wave. In this case, what we say that in a longitudinal wave, the disturbance is parallel to the direction of energy transfer. In other words, my particle shakes left and right, and the wave moves from left to right. Now, in this case, there's only one particular direction it can be going in, left and right there. We are parallel. Okay, and parallel in this sense is very much opposite to the term perpendicular, which we use for the transverse wave. Now, there aren't that many examples of longitudinal waves, but the key one is sound. Sound waves are longitudinal waves, and we're going to look at this in more detail. Put briefly, the particles are moved backwards and forwards via vibrations, and that generates the sound waves that we hear. So when you're generating a sound, be it by hitting a drum, playing an instrument, anything like that, you're vibrating the air. The air molecules move left and right, and that spreads a wave from, say, the left to the right, from the source to the receiver. So that's transverse and longitudinal. Okay, they're both very similar in terms of the fact that they carry energy from one place to another, but the difference here is the direction of the disturbance. And I do think you need to take the time just to sort of think about that before we move on. Okay. If you are ready, then feel free to go on to carry on watching this video to see an example which applies to earthquakes. Now, when we experience earthquakes, one thing we find are different types of waves, and two of the types of waves are S and P waves. Now, an S wave is a secondary wave, and P waves are the primary waves. And what happens when we detect an earthquake? We sense the P wave first, because it moves quickly, but then that's followed up by an S wave. Now, in this picture, again, not mine, you can look at the byjus.com website for any more on this. What you'll notice here is a difference in terms of the disturbance. Okay, in both cases, the waves are moving from left to right. Okay, but hopefully you can see that on the S wave, we've got a disturbance which is up and down, or in other words, 90 degrees to the direction of energy transfer. The one on the bottom is slightly different. So what I'd like you to do at this point is to think which of these is transverse and which of these is longitudinal. And if you pause the video now, okay, have a think, and when you are ready, press play and you'll find the answer. Okay, hopefully you've had a chance to think about that. Answer here is that the top wave is a transverse wave. Our S wave is transverse. And you can see that because, as I mentioned, the oscillations or the disturbances is 90 degrees perpendicular to the direction of the travel of the wave itself. Now the P wave, unsurprisingly, is longitudinal. And you can see there that you've got these areas of high and low density. And if you notice, those, if we were to press play, which we can't here, okay, those are going to move from left to right. And that means that it's traveling in the same direction as the disturbance. Okay, I mainly included this here because by way of finding another example of longitudinal. As I said in the previous slide, longitudinal, there's not many of them. There are lots of transverse ones. If you're asked to give examples, sound isn't always a very good one, but be aware there are other examples. In this case, the P wave, which is also another example of a longitudinal wave. Okay. If you're in my lesson, you should have enough information by now to fill in your table, or you could have done that as we go. Okay, as usual, any questions, please do ask. And if you are happy, you can get on to the next task. Thank you.